Hello, my dear students. Let us continue with the last class, that is Boussinesq analysis. Boussinesq published in 1885 a solution for the stresses beneath a point load on the surface of a material which had the following properties. The first one is semi-infinite, means infinite below the surface, therefore providing no boundaries of the material apart from the surface. Homogeneous, the same properties at all the locations. Isotropic, the same properties in all directions. Elastic, a linear stress strain relationship. You can see here, this is a stress strain graph or a curve. This is for normally consolidated clay or loose sand, and this curve for over consolidation clay or dense sand, and this is for linear elastic assumption. Okay, so now for any theory there will be some assumptions. So let us discuss some of the assumptions made by Boussinesq. He considered the soil medium is an elastic, homogeneous, isotropic and semi-infinite medium which extends infinitely in all directions from a level surface. The medium obeys Hooke's law, that is, stress is directly proportional to strain within the elastic limit. The self-weight of the soil is ignored. The soil is initially unstressed. The change in volume of the soil upon application of the loads onto it is neglected. The top surface of the medium is free of shear stress and is subjected to only the point load at a specified location. Continuity of stress is considered to exist in the medium. The stresses are distributed symmetrically with respect to z-axis. The distribution of sigma z in the elastic medium is apparently radially symmetrical. The stress is infinite at the surface directly beneath the point load and decreases with the square of the depth. These are some of the assumptions made by Boussinesq. Now let us see what he derived, what his theory says. First, Boussinesq solved the problem of evaluating stress at a point inside soil mass due to a point load acting on the surface of soil mass. Now you can see here the point load is acting at this point. This is the ground surface. This is a soil mass subjected to the vertical stress, horizontal stress, or vertical pressure, horizontal pressure. And here there will be, this is the horizontal stress and vertical stress, and there will be a shear stress in this direction, tau gamma z. Okay, so what he considered, let a point load Q, single concentrated vertical load, acts at the ground surface that I showed here, acts at the ground surface here. Okay, at a point O, which may be taken as the origin of XYZ axis as shown. The point O, this is the point O, okay, as taken as the origin of X, Y and Z axis. Let us find the stress components at a point P in the soil mass having coordinates x, y, z, or having radial horizontal distance r and vertical distance z from the point Q. This is the point, and this is a vertical depth, that is a z, and this is a radial distance r. Okay. Boussinesq showed that the polar radial stress may be expressed as this equation: sigma r equal to 3 divided by 2 into q divided by pi into cos beta divided by r square, where r is polar radial coordinate of point P, that is equal to square root of r square plus z square, that is equal to x square plus y square plus z square to the power half, and cos beta equal to z divided by r. In the cylindrical coordinates, the corresponding vertical stress sigma z and tangential stress tau gamma z are given by this equation. Okay, so this you just remember, no need to by heart all these things. Finally, you should know this equation to solve the numericals. Okay, that is sigma z is equal to 3q divided by 2 pi into z cube divided by r square plus z square to the power 5 by 2. When you simplify this, we will get 3q divided by 2 pi z square into 1 divided by 1 plus r divided by z square to the power 5 by 2. So these two equations you can remember, you have to remember. Then tau, that is nothing but shear stress, that can be calculated by using this equation, this or this, 3q divided by 2 pi into r into z square divided by r square plus z square to the power 5 by 2, that is equal to 3qr divided by 2 pi z cube into 1 divided by 1 plus r divided by z whole square to the power 5 by 2. Okay, it should be emphasized that although both the vertical normal stress and shearing stresses are independent of the elastic constants, that is E and mu, Young's modulus and Poisson's ratio, they are very much dependent on the assumptions of linear elasticity. So equation may be rewritten as, you can write in terms of this equation also, sigma z is equal to kb into q divided by z square, where kb is equal to Boussinesq influence factor, that is equal to 3 divided by 2 pi into 1 divided by 1 plus r divided by z whole square to the power 5 by 2. Okay, so this is the equation simplified in this equation. I have written in terms of b. Okay, kb is nothing but the Boussinesq influence factor. So you can use either this equation or this equation. Anything is fine. Now, let's this influence factor. Influence factor is a function of R divided by Z ratio, which is dimensionless and is referred to as Boussinesq influence factor. Gamma divided by Z ratio, that is dimensionless and is referred to as the Boussinesq influence factor. It should be noted that the expression for Z is independent of elastic modulus E and Poisson's ratio mu. That is, stress increase with depth is a function of geometry only. The influence factors for shear stress can also be found out by multiplying the factor Kb by the ratio R divided by Z. Thus, if it is required to find the vertical stress at a point situated at a radial distance r and depth z below the loaded point, find the influence factor for r divided by z ratio and then multiply it by q divided by z square to get the vertical stress. The following table gives the values of influence factors. That is, if you have R divided by Z value, you can calculate what is the Kb value. Suppose R divided by Z equal to 0, Kb is 0.4775. R divided by Z is equal to 0.01, then Kb is 0.4773. Like that till 2.6 here there in this table, and also here the table is continued until 6.15. R by Z ratio is equal to 6.15. We will have what is Kb value. So you have to make use of this table while solving the numericals. The intensities of vertical pressure or stress directly below the point load where R equal to 0 on its axis of the loading is given by this formula. Sigma Z is equal to 0.4775 Q divided by Z square. How it is? Because now R equal to 0. R equal to 0, then R divided by Z ratio, that becomes 0. So for the ratio 0, Kb value, this is actually what sigma Z is equal to Kb into Q divided by Z square. So for R is equal to 0, we can refer this table. R divided by Z equal to 0, Kb value is 0.4775. That's why here it is written sigma z is equal to actually kb into q divided by z square. Kb is equal to 0.4775 q divided by z square. The horizontal radial stress component sigma r and the displacement u, v and w in x, y and z directions are given by the following equations. Okay, this is just you should know all these equations. What is for horizontal radial stress and what is for the displacement u, v, w. Okay, just go through this. No need to study in detail. Yeah, here that's why I have mentioned here. This is mainly based on this equation kb into q divided by z square. Next, let us see the pressure distribution diagram. The Bose-Einstein equation may be used to draw the three types of pressure distribution diagram. The first one is the stress isobar or isobar diagram. The second one is vertical pressure distribution on a horizontal plane at depth of z below the ground surface. The third one is the vertical pressure or stress distribution on a vertical plane at a distance of r from the load point. So these three cases you have to study how to draw pressure distribution diagram. The first one is isobar, second one is vertical pressure on a horizontal plane, and third one is vertical pressure on a vertical plane. Let us see the first one, that is isobar or pressure bulb. An isobar is a line or contour joining points inside soil mass at which the vertical stress have same value. You can see here these are all the isobars and this is the lines of equal vertical pressure or isobars. In other words, an isobar is a stress contour or a line which connects all the points below the ground surface at which the vertical pressure is seen. It is nothing but the line which connects the points, all the points below the ground surface where the vertical pressure is having the same value. Any number of isobars can be drawn as shown in the figure for any applied load system. This is the loading system. Each isobar represents a fraction of the load applied at that surface. Since these isobars form closed figures, you can see here this is a closed figures and resemble the form of a bulb, they are also termed as bulb of pressure or simply the pressure bulb. Okay, because it is closed figure and it looks like a bulb, so it is also called as bulb of pressure or pressure bulb. Normally, isobars are drawn for vertical, horizontal and shear stresses. The one that is most important in the calculation of settlements of footing is the vertical pressure isobar. Pressure at points inside the bulb are greater than that at a point on the surface of the bulb, and pressure at points outside the bulb are smaller than that value. Okay, so the pressure inside the bulb are greater always than compared to the outer the pressure at the outside. A system of isobars indicates the decrease in stress intensity from the inner to outer ones. When an isobar is rotated about the axis of loading, a volume is generated which is referred to as a pressure bulb. The pressure bulb is of great significance in practice. The depth of the pressure bulb of intensity 0.1 Q to 0.2 Q, where Q is the loading intensity at the surface, varies generally from 1.5 times to 2 times the width of the loaded area and is taken as guideline for determining the significant depth for site exploration. Let us consider, suppose an isobar of value sigma z is equal to 25% of q, that is 0.25% of q per unit area is to be plotted. Then we have this equation kb is equal to sigma z why this is, see, actually the equation is sigma z is equal to kb into q divided by z square, but now we'll write in terms of kb, that is equal to sigma z into z square divided by q. Now q is 0.25%, so substitute, so 0.25 q z square divided by q equal to 0.25 z square. We'll continue in the next class.